Welcome to this hands-on tutorial on LightRAG, a simple and fast graph-based retrieval-augmented generation framework. In this video, we will first walk through the 7 core ideas behind LightRAG, then install it on a real machine using OpenAI's GPT-5 models and a Qdrant vector store, run it end-to-end, look at the knowledge graph it builds, and finally review the issues we hit along the way and how we fix them. Here is the published architecture from the LightRAG paper. On the left, raw documents are chunked and handed to a large language model that extracts entities and relationships. Those become a knowledge graph. On the right, a dual-level retrieval paradigm turns a user query into low-level and high-level keys, matches them against the graph and its vector embeddings, and feeds the result to the language model to write the answer. Over the next 7 slides, we will unpack each of these ideas one at a time. Let's start with the problem. Conventional retrieval-augmented generation chops a corpus into flat text chunks and retrieves the few that look most similar to the question. That works for simple lookups, but it breaks down when an answer depends on relationships between entities. Because each chunk is isolated, the system returns fragments and the model struggles to stitch them into one coherent, connected answer. LightRAG fixes this during indexing. For every chunk, the language model performs 3 steps. First, recognition. It extracts entities and the relationships between them. Second, profiling. It writes a short key and a summarizing value for each node and edge, so retrieval is fast and precise. Third, deduplication. Identical entities and relations from different chunks are merged. The result is one compact knowledge graph instead of a pile of disconnected text. At query time, LightRAG works on 2 levels at once. Low-level retrieval focuses on specific entities and their direct attributes, perfect for detailed, pointed questions. High-level retrieval focuses on broad topics and themes that span many entities, perfect for conceptual questions. By extracting both low-level and high-level keys from a single query, LightRAG covers detail and big picture together. Those 2 levels combine into 5 query modes you can pick per request. Local uses only low-level keys. Global uses only high-level keys. Hybrid uses both. Naive skips the graph entirely and does plain vector search. And Mix blends the knowledge graph with vector retrieval, which is the recommended mode, especially when paired with a re-ranker. How does retrieval actually run? LightRAG extracts local and global keywords from the query, then uses a vector database to match local keywords to candidate entities and global keywords to relations. Finally, it expands the result by pulling in one-hop neighbors from the graph, adding higher-order relatedness. This fusion of graph structure and vector search is what makes retrieval both relevant and efficient. New data arrives all the time, and rebuilding an entire index is expensive. LightRAG processes new documents with the exact same graph indexing steps, then merges the new nodes and edges into the existing graph as a simple union. No full reprocessing, no disruption to what is already there. The knowledge base stays current while old connections remain intact. All of this adds up to a big efficiency win, where GraphRAG builds community summaries and traverses them with hundreds of API calls and hundreds of thousands of tokens. LightRAG retrieves with a single API call using fewer than 100 keyword tokens. Cheaper, faster, and it adapts to new data without a costly rebuild. That is the whole pitch, simple and fast. Now let's get LightRAG running on a real machine. We'll wire it to OpenAI's GPT-5 family for the language model and embeddings, and to a Qdrant container for the vector store. Here is the deployment we built. Entity extraction, which makes the most calls, uses the cost-effective GPT-5 Mini. Keyword extraction uses the cheapest tier, GPT-5 Nano. The final user-facing answer is generated by the latest flagship, GPT-5.5. Embeddings use text embedding 3 small, the compact 1600 dimension model, vectors live in Qdrant, while the key value store, the graph, and document status stay in local files. Because all the heavy lifting happens through the OpenAI API, no GPU is required. Installation is 6 commands. First, pin Python and with asdiff and create a virtual environment. Second, install LightRAG with the API extra plus the Qdrant client. Third, build the web interface with Bun, because a source install does not ship it pre-built. Fourth, start the Qdrant container. Fifth, write the .env file with your models, embedding dimension, and Qdrant URL. And sixth, launch the server, which serves both the REST API and the web interface on port 9621. After the install finishes, we have LightRAG version 1.55 in the local virtual environment, along with the OpenAI client and the Qdrant client. Notice there are no Torch or HKUDS packages, because this is an API-only deployment. With the server running, let's use it, first from Python, then through the REST API and the web interface. Using LightRAG from Python takes 4 steps. You construct the LightRAG object with a working directory and your model functions. Then, and this is the single most common mistake to avoid, you must await initialized storages before doing anything else. After that, you insert text, which triggers extraction and embedding. And finally, you query with a mode like mix. Don't forget to finalize storages on the way out. A quick health check confirms everything is wired correctly. The server reports the web interface is available. The language model is GPT-5 mini. The embedding model is text embedding 3 small. And the vector storage is Qdrant, namespaced to the LightRAG demo workspace. Importantly, LightRAG created its own collections right next to the pre-existing ones, leaving them untouched. Here is a full round trip. We insert a short document, which LightRAG processes in the background. Then we ask a question in mix mode. Retrieval pulls 14 entities, 13 relations, and the relevant chunk, and GPT-5 writes a grounded answer, complete with a citation back to the source file. LightRAG also ships a web interface. The Documents tab shows everything you have ingested with live processing status. There are also built-in tabs for the knowledge graph, interactive retrieval, and the API documentation. For this local demo, authentication is disabled, so you land straight in. And this is the payoff. The knowledge graph live extracted from a single short document, 14 nodes and 13 edges, centered on the LightRAG node and the dual-level retrieval paradigm node. The counts match the extraction logs exactly, so we can see the concepts from the first half of this video actually working on real data. Now the issues we hit, because real installs are never perfectly smooth. The first was sneaky. Every query came back saying no relevant context found, even though retrieval was clearly succeeding and finding 14 entities. The real error was downstream. GPT-5 returned a 400 because the reasoning effort value minimal is not supported by that model. Since the setting applies to every model role at once, and GPT-5 mini accepts minimal but GPT-5 does not, the fix was to use low, the tier both models share. After that, queries returned grounded answers. 3 more gotchas worth knowing. First, the repository's default model, GPT-5 mini, was not available on our API key, so always validate against the model's endpoint before writing config. Second, the web interface is not ship pre-built. You have to run the bun build and then restart the server. And third, the Qdrant container had been stopped, so we started it and used a workspace name to keep our collections cleanly separated from existing data. That's a complete tour of LightRAG, from its 7 core concepts to a working install on GPT-5 and Qdrant, a real knowledge graph, and the fixes for the issues we hit. This tutorial was created by Omar Kamal. LightRAG is open source from HKUDS, and full credit goes to the authors of the LightRAG paper. Thanks for watching.